Welcome back to Differential Calculus. In this video, I wanted to introduce you to the second derivative test. I still have vivid memories of being a student and struggling with the second derivative test, not because it's challenging. In fact, it's a very simple test to perform, but because there's a lot going on and it's easy to get mixed up because it's a whole bunch of rules to just keep in your head. And so I want to take the time to slowly go through the theory of what, why, and how we're doing things before we get into an example. And I encourage you to write this down somewhere that you can have it on reference. The idea of the second derivative test is that we are going to be using concavity to classify extrema. And the idea here is actually a lot more straightforward than it seems. If you think about a curve that is concave up, and you think about an extreme value that appears on that curve, well, graphically, it has to be a minimum, not a maximum. And in the reverse, if we have a curve that is concave down, then any extrema that occurs there has to be a maximum and not a minimum. Before I move on, I want to make sure that I am not overstating my case. It is not the case that every relative minimum occurs at a point where the function is concave down. And in fact, I can think of a pretty simple example of a curve that maybe does something like that. Right? This curve is concave down, but not really concave up or down at that point, which is a cusp. So you have a minimum here that occurs at a place where the function is not concave up and also not concave down, right? At that point, there is no concavity to find. This is what we call a cusp. This is a place where a derivative is going to break down and do some weird things that we don't like. All right. So I do not want you to try to remember that minimums only occur when you're concave up. That's not the case. The other direction of that is where things work. If the function is concave up, then extrema is not a maximum. And if the function is concave down, then extrema is not a minimum. This tells you what is not going to happen. At a point of inflection, a point where you're neither concave up nor concave down, anything goes. I've sketched here a minimum. I could also sketch a point of inflection can occur at a place where the function is kind of straight. There is neither a maximum nor a minimum occurring there. And that is kind of the inconclusive case. All right. So that gives us the tool we need. If we have a point that is a candidate to be an extreme value, a critical point from the first derivative, and we know the second derivative, we know the concavity at any given point, then we can use that as a comparison to determine if that point is a maximum or a minimum. If you get that the second derivative is 0, it's neither concave up nor concave down, the second derivative test is inconclusive, and you'll want to go back to the first derivative test that we've used before. And that kind of gives us to an interesting question. If the second derivative test can be inconclusive, why would we use it over the first derivative test? The answer to that is kind of a vague, well, because we can. If you happen to already know the second derivative of the function, or you need to know the second derivative of a function for some other purpose, then this becomes a very easy to accomplish test. It turns out that it's fairly simple to program a computer to compute the first derivative and second derivative numerically, which means that the second derivative test is fairly simple for a computer to handle. But if you don't already have the second derivative and you're trying to work things out by hand, the second derivative test is often not the best way to do things. A little bit later on, probably the next video, we're going to look a little bit more closely at situations where we might know that we're going to need the second derivative and jump to the second derivative test, even though the first derivative test might be more useful. For this video, we're just going to assume that that's going to be the case. We're going to use the second derivative test, and we're not going to worry about whether it's the most efficient tool or not. All right, let's clear out some space. Let's take a look at a function. How about f of x equals 5x cubed plus 3x squared minus 9x plus 7? You might recognize this function. We analyzed it previously. We know that the first derivative of this function is 15x squared plus 6x minus 9. And we know that the second derivative of this function is 30x plus 6. We determined the intervals where it's concave up and concave down, but this much is good enough for our purposes. Knowing the first derivative, we can find critical values by setting this function equal to 0, 15x squared plus 6x minus 9 equals 0. I'm going to take the creative approach and first divide both sides of the equation by 3. Let's see, 5 times negative 3 is negative 15. Two numbers that multiply to negative 15 and add to positive 2 are 5 and negative 3. So this is going to factor pretty nicely. It's also going to factor really nicely because the only way to factor 5x squared is as 5x times x. The only way to factor negative 3 is either 1 times 3 or 3 times 1. So just checking, let's see, if I put the minus 3 over here, that would make this plus 1. Our middle terms would be plus 5x minus 3x, which add to negative 2x. That works out perfectly. And solving from there, I get that x equals 3/5 and x equals negative 1 are our critical values. Now, to test these, we are going to go to the second derivative. F double prime of 3/5. Well, 30 times 3/5 is 18. 18 plus 6 is 24. The only thing that matters is that that is greater than 0. That means that the function is concave up. And when the function is concave up, extrema have to be minima. So we have a local minimum at x equals 3/5. Then trying with -1. F double prime of -1 is going to be -30 plus 6, -24. Again, the only thing that matters is that that's negative. It's less than 0. Less than 0 means concave down. Concave down means that our critical value has to be a local maximum. Right. Is this easier than the first derivative test? I talked about that earlier, but again, probably not. The particular function that we're working with here is a polynomial. Polynomials are great because they're fairly easy to work with regardless. But the important thing here is that we already had the second derivative. If we had a less pleasant function, if we had a rational function where taking the derivative itself would be a challenge, I would be far less inclined to use this sort of analysis. But we have the second derivative, and evaluating a function at a point is very easy. It's a nice, quick way of determining the representations of your critical values. I'd like you to look at a similar problem. Once again, a function that you should already be fairly familiar with. F of x is x to the 5th minus 5x cubed. And I specifically want you to use the second derivative test to classify critical values as maxima, minima, or inconclusive. So in practice, if you end up with a point where the second derivative test is inconclusive, you do go back to the first derivative test. You test a point slightly above and slightly below the critical value. You check to see if the function changes from positive to negative or from negative to positive to classify your extrema. I don't want you to take that step on this problem, although I will do that in the solution video. It's a little bit more time than I want you to spend on this. All right, take a couple of minutes, see what you can do with that, and I'll see you in the next video.